Picture this, a universe of technology and innovation, all condensed into a tiny chip. That's the power of semiconductors. These tiny marvels, straddling the line between conductors and insulators, are the unsung heroes of modern technology. They're at the core of everything electronic we touch, from our smartphones to the most advanced supercomputers. In essence, semiconductors are the Goldilocks of materials, perfectly balancing the flow of electric current in electronic devices. So, what exactly makes a semiconductor tick? It's all down to atoms and their bonds. Imagine a universe of atoms intricately arranged in a crystal lattice. Each atom in this lattice has 4 electrons in its outer orbital. Why 4, you ask? Well, this specific number allows for the formation of covalent bonds, a type of chemical bond where electrons are shared between atoms. This sharing of electrons results in a stable balance, creating a material that isn't quite a conductor, but not an insulator either. Now picture this. Let's say we have a solid piece of silicon, a popular semiconductor material. Its atoms are arranged like a well-organized army, each sharing its outer electrons with 4 neighboring atoms. This leads to a balanced state, with no free electrons to conduct electricity at absolute zero temperature. However, as we increase the temperature, some electrons gain enough energy to break free from their bonds, leaving behind positive charges, or holes. These free electrons and holes can move around the lattice, conducting electricity. This, my friends, is the magic of semiconductors. They're not just sitting there letting electricity pass through them or blocking it altogether. They're actively participating in the process, controlling the flow of electric current in a dynamic and adaptable way. It's this delicate balance, this dance of atoms, electrons, and bonds that makes semiconductors so fascinating. These tiny chips are truly the unsung heroes of our digital age. This unique atomic structure allows the formation of the semiconductive material. Now here's where things get interesting: the process of doping. Doping in this context doesn't involve any athletic scandals. Instead, it's a key step in the creation of semiconductors. By introducing tiny amounts of certain impurities into the crystal lattice of the semiconductor, we can significantly alter its properties. Think of it like adding a pinch of salt to a dish, transforming the flavor entirely. These impurities, often elements like phosphorus or boron, can increase the number of free electrons or create holes where an electron should be. This results in 2 types of silicon: N-type, which has extra electrons, and P-type, with its characteristic holes. When an N-type and a P-type silicon come together, they create an interesting effect. The extra electrons from the N-type rush to fill the holes in the P-type, creating a barrier that controls the flow of electricity. By manipulating the semiconductor in this way, we create the basis for semiconductor devices like diodes and transistors. So, what happens when we put these doped semiconductors to work? Well, let's start with diodes. Picture a one-way turnstile at a subway station. It lets people in, but not out. Diodes do the same for electrons. They allow current to flow in one direction, but block it in the other. This property is crucial in many electronic devices, converting alternating current into direct current. Now let's talk about transistors. Think of them as supercharged diodes. They can act as switches, turning the flow of electrons on or off, or as amplifiers controlling the amount of current that passes through. They're like the traffic cops of the electronic world, directing the flow of information within a device. But where the magic really happens is when we scale up. Imagine a silicon chip, smaller than a fingernail, packed with thousands, even millions of these tiny transistors. This is how we create microprocessors, the brains behind our computers, smartphones, and countless other electronic systems. As we continue to refine and miniaturize these components, we pack more and more power into smaller and smaller spaces. This is how we've gone from room-sized computers to devices that fit in the palm of our hand, and why technology has become such an integral part of our daily lives. It's this constant refinement and miniaturization that have made technology so ubiquitous in our lives. Next time you're swiping on your smartphone or firing up your laptop, remember what's powering it. The omnipresence of semiconductors is a testament to their importance. These tiny chips are the unsung heroes of our digital age, making possible the devices we use every day. They've transformed our world, revolutionizing communication, entertainment, and even medicine. From the smallest smartwatch to the most powerful supercomputer, the influence of semiconductors is pervasive. Remember the humble semiconductor chips silently powering it all,